Hello, my name is Kevin O'Connor, and this is Kara Clark. And today we're going to take you through the steps to conduct a riverine CRAM assessment. We have chosen Alameda Creek as an example area.
An important part of conducting the CRAM assessment is to collect background information on the site that you want to assess. We're here at Sunol Regional Wilderness, and we've talked to fisheries experts as well as local park rangers. So we know that this stream has a dam on it and that it also supports trout. We know that there is light recreational use. Equestrians and hikers use the trails in the watershed upstream of the assessment area.
Once you've established your assessment area, but prior to beginning your assessment, you must determine whether you are in a confined or non-confined system. A non-confined riverine system is when the valley width is at least twice the bankfull width, allowing for your channel to migrate. A confined riverine system is when the valley width is less than this. Here at Alameda Creek, we have an example of a non-confined riverine system. This is because even though we have a very steep bank on the left-hand side, on the right bank we have ample room for the channel to migrate across the valley floor. During our initial office assessment, we assumed that the downstream point of our assessment area was going to be located at this bridge. However, upon coming out in the field, we noticed that there is an Arizona stream crossing located just upstream. As a result, we're going to move the downstream point of our assessment area upstream by about 20 meters.
As you can see, this Arizona crossing is maintained for vehicular and horse traffic. They've moved the large boulders from the crossing downstream, which forms a small dam. This makes a pool upstream and creates a significant hydrologic break. Therefore, we need to shift our assessment area upstream so that it does not include this hydrologic break.
After determining our downstream point near the Arizona stream crossing, we took our meter tape and measured bankfull. We obtained a measurement of 25 meters. From this, according to the CRAM rules, the stream length of our assessment area should be 250 meters, which is 10 times bankfull. However, there is a limit between 100 and 200 meters. As a result, for this assessment area, we will default to a 200 meter long length of the stream. Now that we've established the downstream point of our assessment area, we need to establish the lateral width of the assessment area along the entire stream corridor. For the rules outlined in CRAM, you want to include the entire footprint of all vegetation providing allochthonous input or organic material to your active channel. For example, here we have an alder. It's rooted in the active channel, so we will include the entire footprint of all the vegetation from here all the way down to the stream. On my left, there's a maple tree which is rooted in the abandoned floodplain. This tree is providing no allochthonous input to our active channel, so would be excluded from the assessment area. To assess riparian continuity for riverine wetlands, the first step is to draw your assessment area. Once this is complete, extend the average width of your assessment area 500 meters upstream and downstream, regardless of the land cover types that are encountered. Identify all places where non-buffer land cover types are at least 10 meters wide and interrupt the riparian area within an average width of your AA, on one side or the other side of your channel. Add up all of your breaks in continuity upstream and downstream and look to the rating table in your manual. For this particular site, there were no breaks in riparian continuity 500 meters upstream and downstream of our assessment area.
This metric is assessed by looking at the proportion of the perimeter of the AA that has at least 5 meters of buffer land cover. So the upstream and downstream ends are not included in this metric. You only look at the lateral edges of the AA and see what proportion of that edge has buffer adjoining it, based on the table that shows what types of land covers are buffer and not buffer. At this site, the entire perimeter has buffer land cover surrounding it. It has 100% width buffer. This metric assesses the width of the buffer adjoining the AA. Only measure the width where buffer is present. If part of the AA does not have any buffer, do not put any buffer lines there. Extend 8 lines laterally away from the edge of the AA, evenly distributed. If there is 100% buffer, you will have 4 lines on each side of your creek. However, if part of the AA does not have buffer, you might have some other distribution of lines around your assessment area. Measure the width of each line and average the 8 lines to get a score for the average buffer width. At today's AA, we have 250 meters of buffer in all directions, so we get an A for average buffer width. We're here on the right bank of Alameda Creek in the buffer zone for our assessment area. In order to assess buffer condition, we're going to look at the presence of native and non-native vegetation, any soil disturbance or compaction, and human visitation. We have a nice overstory of native trees, oaks and sycamores. So we have some non-native grasses in the understory. There's a road that's used by vehicles, horse traffic, and hikers. We have evidence of horse traffic. Based on the narrative table, I would assign this buffer a score of a B. The water source metric assesses anthropogenic alterations to water sources that affect dry season flow. In general, you look at the watershed upstream within 2 kilometers and assess how much of that has irrigated agricultural land or developed land. You can see from the aerial imagery that Alameda Creek is relatively undeveloped within the immediate watershed upstream about 2 kilometers. Therefore, this assessment area gets an A for water source.
When assessing channel stability, you'll want to walk through your entire assessment area and look for indications of equilibrium, degradation, and aggradation. Here at Alameda Creek, we have 6 examples of equilibrium. In our pools, we have a good amount of leaf litter. We have an embedded woody debris that is of the size that's appropriate for this stream. On our channel bars, we have well-sorted bed material. In the stream channel, there are pools and they're regularly spaced. Along the edge of the stream, there's very little active undercutting or burial of the riparian vegetation. And finally, we have a well-defined bankfull contour, as described earlier. While the majority of the indicators of channel stability at this site are for equilibrium, there is one indicator for aggradation, that being the presence of perennial riparian vegetation on the channel bars. Here on the right bank of Alameda Creek, we have several indicators of bankfull. Here we have a young bay laurel and a young pine tree. Here we have some mosses at the lower edge of the terrestrial vegetation, transitioning down to the active channel with fresh splays of sediment. I would put bankfull right here. Here we are on the left bank of Alameda Creek, looking for our bankfull contour. The indicators are slightly more obscured on this side due to the steepness of the terrain and the presence of large boulders. However, we do have a transition from upland vegetation down into more wetland vegetation. I would place the bankfull about here and then confirm its location with the elevation on the opposite side of the stream. Now that we've established where the bankfull contour is located, we need to measure the bankfull width. It's important to do this in a location along your stream reach where there are no pools or meanders that would exaggerate your entrenchment contour. Place a meter tape at the estimated bankfull contour and have your team member extend it across the active channel. Once you get your bankfull height, double it to get your flood-prone height. Then re-extend your meter tape to get your flood-prone width. The ratio of the flood-prone width divided by the bankfull width gets your entrenchment ratio.
The structural patch richness metric is a tally of the number of physical patch types present in the assessment area. This metric is different from the topographic complexity metric in that it assesses the number of patch types, whereas topographic complexity assesses the interspersion and overall variation of patch types in the assessment area. Flood flows in the creek have left an accumulation of wrack piled along the base of the trees at a high water line. The wrack is composed of leaf litter and small woody debris, and it provides habitat for invertebrates and organic material to the creek. Bank slumps and undercut banks are lumped together into a single physical patch type. Here we have a nice example of an undercut bank. The stream has scoured out an area. This forms nice habitat for fishes and invertebrates and adds a shaded area to the stream. This is a good example of cobbles and boulders. A boulder is larger than 25 centimeters, provides habitat for fishes, shading, and for macroinvertebrates. It indicates that the stream has high energy and it can oxygenate flowing water as it comes through the stream. Cobbles have a smaller diameter, but also form important habitat for macroinvertebrates and other biota. This is a high energy creek. It's able to transport large material, such as this log, which then catches any other debris that's coming down in a flood, creates a debris jam. The debris jam alters the flow of water and sediment. It forms a scour pool, which creates habitat, and it adds complex physical structure to the creek. This is a great example of large woody debris. It's a log greater than 30 centimeters in diameter, more than a meter long. It forms an important structure in the creek. A pool is an area of much deeper water compared to the rest of the channel. The pool retains water during low flow and so can be a refuge for fishes or invertebrates. Pools often form below riffles in a pool-riffle sequence. As is the case here, we have a riffle above coming into a pool, a glide, and another riffle below us. Hummocks are mounds that form along the banks and floodplains of fluvial systems. They are created by the collection of sediment and organic material around plants such as sedges. This forms a mound-like structure, usually less than a meter high, that adds to topographic complexity and overall physical structure. This is a nice example of a point bar. It's formed in a straight reach of the creek. It's a convex feature with finer sediments on the top and coarser sediments lower down. Point bars may support vegetation. In this case, we have some alders growing on the point bar. At the bottom of the point bar, it's anchored by a boulder that catches the transient bedload sediment as it comes down the stream and forms this nice feature. A variegated shoreline resembles a meandering pathway along the edge of the stream. Variegated shorelines provide greater contact between the water and the land. Here we have a stump and a boulder that add complexity to the shape of the shoreline. Riffles are areas of relatively rapid flow in the stream. They form in high gradient reaches. They flow over cobbles and boulders, which adds oxygen to the stream. They are important habitat for fishes and aquatic invertebrates. This secondary channel conveys flood flow in the creek. It adds topographic complexity. It provides a moisture gradient from the upland into the main channel. And it may form a pan or pool in the wetter season.
When assessing topographic complexity, you're going to want to walk from one edge of your assessment area all the way across the channel to the opposite side of the stream, looking for the number of benches and breaks in slope and the overall microtopographic complexity formed by boulders and logs and hummocks and things like that. When assessing topographic complexity, you'll want to select 3 representative cross-sections within your AA and draw them in your field book. You'll then compare those 3 cross-sections to images in the field book and the corresponding narrative descriptions. Here at Alameda Creek, I'm going to walk a typical cross-section and describe the micro and macro topographic features that I am seeing. Here on the right bank, just above bankfull, we have one bench. We then have a steep drop-off to a secondary bench represented by this sandy feature. Continuing across the stream, we have a large mid-channel bar covered in lots of cobbles, some down woody debris, and several hummocks. Coming off of the berm, come to the low flow channel, the thalweg, which is the deepest portion of the stream. Again, we have lots of cobbles and boulders along the edge of the stream, and some downwoody debris, several hummocks, and some exposed bedrock. You can walk up onto two benches, this being the first, this being the second, two separate elevations, indicating a high amount of both microtopographic complexity and macrotopographic complexity.
The plant community metric assesses the number of plant layers, the number of codominant species, and the proportion of those that are invasive. Here on the left bank of Alameda Creek, we have examples of all 4 plant layers. We have a short layer, less than half a meter, this sedge, Carex nudata. We have a medium layer, between half a meter and 1.5 meters, this poison oak. We have a tall layer, 1.5 meters to 3 meters, this sapling alder. We also have a very tall layer, greater than 3 meters, these alders that are lining the banks of the creek. The next step is to determine the number of codominant plant species in each layer. This is based on relative cover within the layer. Any plant species that is more than 10% relative cover in that layer is counted as a codominant species. The final step in the plant community metric is to determine the proportion of plants that are invasive. CRAM standardizes the invasive status determination by using the California Invasive Plant Council list. However, local experts can identify invasive plants in their region and designate those as invasive as well. At this assessment area, we had 5 codominant species, 4 plant layers, and none of the plant species were invasive. The horizontal interspersion metric looks at the number of plant community zones and the interspersion or amount of edge between them. Here at Alameda Creek, we have a Carex zone in the active floodplain. We also have a blackberry poison oak zone in the drier bank. And finally, we have an alder zone lining the active channel. The vertical structure metric assesses the amount of overlap across the entire assessment area. Abundant overlap is where 3 plant layers are overlapping each other. Here is a great example of that. We have an understory of Carex, we have a tall alder, and then we have a very tall oak tree above, which constitutes 3 layers, which makes abundant overlap. Over here, we have the very tall oak with the Carex understory, which is 2 layers, only moderate overlap. This metric then looks at the amount of moderate or abundant overlap across the entire assessment area. So it integrates the horizontal and vertical dimensions.
We hope you enjoyed the training and found it very informative. For more information, please see our website.